Merci, bonjour à tous. Bienvenue au dernier séminaire StatCam de la session. Donc, nous sommes heureux de vous accueillir. Donc, aujourd'hui, nous avons l'honneur de recevoir comme invité le professeur Jiguo Cao, la prononciation importante. Donc, yes. Yeah, merci. Donc, il nous reçoit de l'Université Simon Fraser, donc, où il est présentement professeur au département de mathématiques et d'actuariat. Professeur Cao a reçu le prix CRM SCC en statistique en 2021 pour l'excellence en recherche, en particulier en recherche collaborative, notamment pour la formation des étudiants et puis l'encadrement, la supervision des postdocs. Il a obtenu un doctorat en statistique à l'Université McGill. Donc, il connaît très bien la ville de Montréal. Il a notamment côtoyé des collègues qui sont ici, notamment Geneviève. Donc, voilà, ses intérêts de recherche incluent l'analyse de données fonctionnelles, la statistique génétique, l'analyse d'images, l'inférence statistique pour des modèles dynamiques complexes. Donc, aujourd'hui, il va nous parler de functional neural networks.
Thank you. Yeah. First, I want to thank the department for inviting me here. I know many people here. Cedric was my postdoc before, and we work very closely now. And so I also have very two old friends, Geneviève and Julie. We did our PhD together at the McGill University. I came to the study at McGill in 2003. And that's my first time I go abroad. So Montreal for me is like a hometown in North America. So I really like this city. I enjoyed my life here. It's very nice for me to come here and visit the city and also visit with friends, catch up. That's a very nice trip. I'm going to talk about our recent work about neural networks. So my research area is mainly on we call functional data analysis. Some of you know Jim Ramsey for a long time. So I did my PhD together, PhD with unsupervised Jim Ramsey. So my research area is functional data analysis. So if you're not familiar with functional data analysis, here I'm going to show you some pictures. So on the left side is the daily average temperature in Vancouver, in 35 cities in Canada. So because of the temperature is observed a long time, so we can treat the temperature as a function of time. So that's we call it functional data. So each curve here is one piece of functional data. So instead of look at each individual temperature at each time point, we will look at the whole curve as one single data point. So that's kind of a unique perspective for functional data analysis. The right side is the image, a brain image. So basically the image you can understand as kind of a function of the spatial locations of the brain. So this can be understood as a bivariate functions. So therefore we can also treat the image as a functional data as well. And yes, so this is kind of two examples for functional data. And so generally when we write down the functional data, we will write down as a function of time, like X, I, or T here. Suppose we have n curves or n image. Okay, so if you want to get an introduction about functional data analysis, Jim Ramsey and Silverman has a very nice book about this topic. So before we talk about functional neural networks, let me just give you a quick introduction about the neural networks in general. So Montreal is one of the central of deep learning. So deep learning now become very hot topics and very powerful tools as well. And so basically this deep learning is kind of a type of neural networks. Neural networks have been started like in late 90s. So now so then it become like very hot around 2000, and then like become less popular in 2010 around, and then now it's become hot again. So basically the deep learning is neural networks with more layers and modules. Okay, so the things I like deep learning or neural networks is that they are some nonlinear models of the data. So, and also they take care of the hierarchical structures. And so it's a very, very naturally to model the data in some nonlinear way. And also the model tend to be very flexible and can be taken with any input output type of data. So why deep learning is so popular now? Maybe because like we have better algorithm, also better computing resources available. So also now we have big data, like we have big image data sets with the labels. So now we are able to treat a very large neural networks with enough data set. Okay, and there are also a lot of open resources available, like TensorFlow, PyTorch. So this is a one classic applications of deep learning. It's called a generative models. So yeah, so Cedric and I also always want to touch this topic, and we have a very nice conversation this morning about how we can do the generative models. So this is a kind of people working on to generate the fake faces. So like on the very right side, it is like the result in 2019. And you can see the face is a fake face, but it looks very, it's like real, right? Yes, yeah. So it's a very powerful, amazing results getting from this deep learning. So in terms of the math behind this neural networks, so I will give you some math details. So this is kind of one artificial neurons. And so basically you can see here for these neurons, we have like n input, x0 to xn, right? And then we have a weight, and we do the weighted average of the input. And we have like a b, the intercept term, and it's called a bias in neural network literature. And we do these linear combinations. We got this z, and then we do a nonlinear transformations of this z to the output f. So here, this g is an activation function. So generally, we will use the nonlinear activation functions. You can also use the linear activation function as well. So you can see the form is very simple, right? So it's basically is a nonlinear transformations or linear combinations of the input. Okay, and so you can also have multiple neurons. So so basically, suppose here you have like a k neurons now, and so basically each neuron will be these linear combinations of this input. So now this W become a matrix, and then this is vector Z. You will do this nonlinear activity function. You will get the output F. Yes. So this is kind of the general forms for these neural networks. By the way, so if you have any questions, you can interrupt me anytime. I'm okay to answer questions. So yes. So I don't prepare many slides. Okay, so and then like what the deep learning powerful is that we can add a bunch of hidden layers. So this is here this H0 to HK capital H minus 1 is called hidden layers. Okay, so basically these hidden layers is a nonlinear transformations of linear combination of the input X, and after we get these hidden layers, we can do another layers of neural networks, and we can do these combinations, and this can become like a very complicated if we can have multiple hidden layers and yes, different structure as well. Okay, so this is the structure of the neural networks. So recent years, I really like the deep learning ideas. The reason is that because it's get such a nice results, right? So must have be some this tool must have very powerful. So when I learn about more about deep learning, and I find that this is a kind of a very good tool for statisticians to use. For the reason is that I feel that for deep learning, I think there's like a two advantage for the deep learning. So the first advantage is that the deep learning is a very good nonlinear approximations for the for high dimensional functions. Okay, so when I did my PhDs here, so we always want to estimate a function non-parametrically, and so at that time we feel that it's very hard to estimate the nonlinear functions for high dimension. So suddenly, like with these deep neural networks, we are able to approximate any dimensional functions just using these linear combinations and doing these nonlinear activation functions. It will works very nicely. So that's the one thing I find is amazing. The second point is that so when we learn the linear regression models, we always at least for me, I feel always confused, how many interaction terms I should use in the linear regression models. And so when we have these neural networks, it seems so natural that, when they do this linear combination of the input, it's very naturally, to handle these interactions between these input factors. So we don't have to worry about, so how many interactions term we should use. We should use a two-way interaction or three-way interactions. So that's the second thing I find is very powerful. So and surprisingly, for this deep learning models, it has so many parameters and working on high dimensional space, but it seems that there's not a dimensionality problem. So it seems able to handle millions of input without no problems. So I'm not sure it have solved the cursor dimensionality problems. So that's kind of to share with you my point of view of deep learning from a statistical research perspective. Okay, so far, like for most literature deep learning, so they assume that the input basically is a long vector. It may be a high dimensional vector, but it's a vector. So we have J neurons to handle with J inputs. And as I just mentioned that, my favorite topic is functional data analysis. So I always work on functions, the curves, the image. So I'm thinking like, maybe I can tailor the neural networks a little bit more careful, for this functional input. Okay, so this is how these functional neural networks come up. Okay, so this is kind of will give you a motivation examples. So here, we have the data of the bike rental data from Washington, D.C. Okay, so we want to predict the number of bicycle rentals based on the average temperature curves. We know that temperature and weather is a key factors for how popular the bicycle is. So like, we are thinking, whether we are able to make this prediction well good enough. So we pick up 102 days. I think in these 102 days, there's no rains. Okay, so basically just the temperature is the factor affecting the bike rental. Okay, so some days maybe have good temperature, some days may be too cold, some days may be too hot. Okay, so want to do the prediction. So you can see here, our input will be this hourly temperature curves. Okay, so this is we call the functional input. So each of our input will be a function. Okay. So we want to predict the total number of bike rental on that day. Okay, so that's our motivating examples. So now let's give you some introduction about the functional neural networks. So basically, when we have this hourly temperature, so what we can do is that, okay, first, maybe we will have the hourly temperature, from hour 1 to hour 24 each day. And so what we can do is that, we can get this 24 hours of temperature as each of the temperature at each hour as one variable. And then we will have the temperature at each time points, right? We can treat it as separate variables. And then we can, put it into the neural networks, and it will do all the trick and do these linear combinations of this input. And then, doing these activity functions, we'll get the output. Okay, so this is kind of how the traditional neural networks will do. We have this n input. Okay, so I'm thinking because now we treat this input as a function of time, right? So if you just think about this input as a function of time, basically we only have instead of 24 inputs. If we just treat it as a general function, this actually means we only have one input xt. Okay, so our input will be just a function xot. Okay, so when we have the input function xt, then we need to take care of this input function xot. Naturally, instead of using the summation, we can use the integral now, right? So the weight parameter here will become a functional weight of functions. Okay, so this w will be a function of t, and then we will do this kind of linear combinations. Now is like product of the weight function times the input xt, and we do the integral. So now this will become a scalar now, right? And then we will get the nonlinear activation function t here, and so we can do the metric in neural networks. We can add in hidden layers, etc., and make this neural network very powerful. Okay, so how do we estimate this functional weights WT? So in functional data, so we generally, when we estimate a function, we will using basic functions to represent this function WT here. So the WT here will be a linear combination with the basic functions. So here, phi1 to phi LOT will be basic functions, and the C1 to CL will be the coefficients for these basic functions. Okay, so now when we estimate these weight functions, we only need to estimate these basic coefficients, because we generally will choosing the basic functions in advance, and then we will fix this phi1 t to phi LOT. Generally, these basic functions are known and pre-specified, and so we just need to estimate these coefficients for these basic functions. Okay, so this is the ideas. So generally, when we're using the basic functions, our favorite basic functions is called a cubic B-splines. So if you're not familiar with cubic B-splines, this just give you pictures. So here, each color represents one basic functions. Okay, so you can see that for this basic function, generally it has a bell shape. Like if you look at it, just the pink ones, okay, it has a bell shape. And also it's only non-zero in small intervals. Okay, this is called compact support properties. And yeah, so it's turned out very powerful. Using these simple basic functions, it can approximate any complex functions pretty easily. Okay, so that's will be most time we will just use the cubic B-splines and the basic functions. Okay, So another thing is that when we using this number basis function to estimate the functions, because these base functions are such powerful, so we have to be a little bit careful to prevent any overfitting problems. So one thing we tried is we will add a roughening penalty on the functions. So so what we did is that instead of besides the likelihood function to estimate the basic coefficients, we also add a we call it roughening penalty term. Okay, so here the roughening penalty term will be just the second derivative of the weight functions and do the integrals or with back to t. Okay, so you can think about like so if WT so if in order to minimize these penalty terms, so for example, the extreme case, the penalty term will be equal to 0, means the second derivative will be equal to 0 on the whole time domains. Means that the second derivative will equal to 0 means the weight function itself will be just a linear function of t. Okay, so we know that for linear functions, it's completely flat, right? So it's very smooth. Okay, so that's kind of how we using these roughness controls.
Excuse me. We have a question in the room. Someone is asking, how do you choose the capital L for the number of coefficients and the...
Okay, capital L, right? Number of basic functions. Yes. This is very good questions. So generally, it's we can try a different number of basic functions, and we can doing the kind of we call it tuning parameters, doing a little bit of tuning and to find the number of optimal number of basic functions, and that will be not easy. Okay, and the reason is that if you familiar with the B-splines, so the number of basic functions will be decided by the nodes location. Okay, so this each of these dashed lines is a location of the we call it nodes. Okay, and also so the number of basic function will depend on the number of nodes, and also will depend on the location of the nodes. Okay, so therefore actually it's not that easy to find the perfect basic functions. Okay, so therefore to simplify this process, what we typically do is that we will using saturated number of basic functions. So for example, here if we have like 24 hours, we will use 24 basic functions. Okay, we will make sure that our basic functions is flexible enough to approximate any nonlinear functions. So when we're using the saturated number of basic functions, the main thing we need to worry now is that we don't want to overfitting the functions. So therefore, like we added this roughness penalty term here. Yeah. So the short answer is that we will using this roughness penalty to penalize to control the smoothness of the function, and we will using the saturation number of basic functions to approximate the G of t. So generally, this L will be very close to the number of observations. Yes. Okay. Any questions? Yes.
So I don't know anything about splines really, but do you ever use other basis functions?
Sorry?
It's just the splines are orthogonal functions, right? I guess.
It's somehow orthogonal, but not exactly orthogonal. Yes.
Okay.
Yeah. Yes. Yeah. Yeah. So
could you use any set of orthogonal?
Yes. Yes. Yeah. So
advantages, because like I saw a talk once, and they made the first basis function kind of in the shape generally of what they wanted to image, and then they created a second basis function. They constructed the basis functions based on what they wanted to image. So does that work out very well, or?
Yes. Yeah. So basically, this is a very good point. So like generally, those basic functions is called empirical basic functions. So the basic function tailored specifically for the data, and so that's like we have like number of methods specifically designed how to estimate those basic functions direct from the data. Mainly the approach is called functional principal component analysis. Okay, it's functional PCA. So that's for those approach is like kind of they are able to just using a very few number of basic functions to approximate the functions. So kind of efficient, but at the same time you have to estimate the basic functions. So that's a little bit actual work. Yes. So that's an empirical basic function method. Another big type of basic functions is called Fourier basic functions. So if you have like periodic functions, and you may using the sine cosine functions to approximate the functions. Yeah. Yes. Yeah. So if you have a non-periodic function, you are using B-splines. Yes. Do you have any questions? Yes.
Go ahead.
Okay. I'm not sure I follow whether the basis functions are fixed or not. Like
in our method, the basic functions are fixed.
okay, and we use the same L for every single layer.
So we were using cubic B-splines, but the location of the nodes will based on the data point we have.
Okay.
Yes. Yes. Yeah. Okay. Yes.
So maybe you said it, but what do the two dots represent on the panel?
This is the second derivative.
Sorry, second.
Yes. Yes. Yeah. Yes. Yeah. Yes. Okay. So this is the how we define the. So we use the second derivative to define the roughness penalty or the WOT. Okay. So now this is for like one functional variables, right? So in the real data, we may have multiple functional covariates, and maybe also have some scalar covariates. Okay, the covariates not collected on multiple time points. So we can easily to generalize the structure, and basically we will have a functional weights for each functional inputs, and we will have a scalar weights for each scalar covariates. Okay, and we can do this construct the neural networks based on this formula. Okay, so this is kind of the general ideas. So we have P functional input and J scalar inputs, so we can do this neural networks pretty easily. Yes. And so when we do the network training, so we need to calculate the gradients. So because here our functional weights is a linear combination of basic functions, so actually it's very easy to calculate the gradients based on the chain rules. Okay. And also, so here, generally our number basic functions is less than the number of time points. So therefore, in terms of the parameters in the neural networks, we're using less parameters than just using the time points as the inputs. Okay, so that's an advantage for these functional neural networks. Another nice advantage for this functional neural network is that we can have better interpretations. So for the conventional neural networks, we will design this estimate these weights automatically based on the optimization, but it's very hard to interpret these weights. Okay, and for the functional neural networks, because we control the weight parameters very smooth, so it's easy to visualize these functional weight parameters. So just here we give you the ideas. Like so, I think this is the bicycle rental problems. So so suppose we have 24 hours of temperature, and so we do the weights on each of these temperature at each hour, and you can see this is kind of the trained weights when we minimize the loss. Okay, so this is the optimal weights we got. Okay, so if you look at these weights, you can see nothing, right? It's like going up and down, and it's hard to understand what these weights stand for. And so if we do this functional weights, so you can see that, so this is the functional weights we obtained for these bicycle rental examples. And you can see here, like, so basically it's a very smooth function, right? And also, like, you can see here, it's kind of peaked around like hour 10 to like hour 8 o'clock in the evening, right? So that's kind of what, like, you know, people using their bicycle most of the time. Yes, yeah. So this is kind of, you know, tell you that basically this temperature at these points are the kind of most important more weights when they do the prediction for the bicycle rentals. Okay, that's kind of easier to understand, you know, where which time period will get the most weights when do the prediction. Okay. Yeah, so we also developed the R package called the FAN, you know, for general use. And so basically you can just tell the inputs, and this package will be able to train the functional neural networks automatically. So now let me show you some results. Okay, so back to this bike rental problems. So we want to predict the number of bike rentals based on the hourly temperature. And so basically our input will be just this temperature curve. And we want to prediction for the number of bike rentals, okay? So we have 102 hourly temperature curves. And so we're using two criterions. The first criterion is to look at like, you know, kind of the R square, okay? This is to see how our fitting is. And the second thing, we look at the prediction accuracy. So we're using the 10-folder cross validations for the prediction. Basically, we validate data to 10 parts, 10 groups, and each time we will using 9 groups to do the model training, and then we predict for the 10th group. Okay. So this is the results. So we tried like, you know, all conventional methods to use, including functional linear model. This is a kind of classical model used in functional data analysis. Basically, it's a linear model. Okay, and we tried other models as well. And so particularly, we also tried like, you know, conventional neural networks. This is feed-forward neural networks. We also tried convolutional neural networks. And so this is the last row is our functional neural networks. Okay, so you can see so this is the prediction, the mean prediction error. So you can see that, so basically our neural network get a very good, the smallest prediction error for these problems, and got the highest R squares, and also pretty small standard error as well. Yes.
Yeah, just had a small question because you didn't mention that, but usually in neural networks, you're supposed to normalize the data you put as in inputs, like they should be on the 0, 1 grid. How do you normalize your function? You just put the function that they are? Or?
Yes, currently we just put the function is
make any transformation.
Don't do any transformations. That's right. Yes. Yeah. Do you think it will make a difference if up to the normalizations first? Okay. Yeah, that's a very good point. We will investigate that. Yes. Yeah. Yes.
Another question about integrals, right? So do you do any sort of quadratures to make computations?
Yes. Yeah. Yeah. So basically, it's like we doing the numerical quadrature methods. Yes. Yeah. So the simple you don't have to make it a very complicated quadrature methods. So you can just using basically it's a weighted average. Yes. Yeah. Yes.
In the input function, I understand that you get the temperature from observation.
Yes.
Right? And so the observation are at discrete points in time.
Yes.
How do you think that contains function?
This is a very good point. So yeah, so generally like we were doing some we call the pre-processing. Okay. So like because of like we have pretty dense observations, so we can do like using we call a spline regression, we can transform these discrete data points to a continuous function pretty easily. Yeah. Okay, so this is the first result. And so again, like I want to show you the interpretations. So this is the weight functions. On the left side is obtained from functional linear models. It's kind of going up and down. Okay, you can see that for our functional neural networks, this is our weight functions. And you can see it's a very simple trend. Okay, and much simpler than this looks like. And you know, we are able to get a very small prediction errors. Yes.
How do you interpret the negative coefficients?
Yes, this is yeah. So I guess like maybe like for example, the negative coefficients, negative weights will means like you know the temperature at this time intervals will have negative effect on the bicycle rentals. Yes. Yeah. So yeah. So I'm like see I don't know. I think that's a very good point. Yes. Yeah. We didn't think about this carefully. Yes. Yeah. Maybe we should interpret this more carefully. Yes. Yeah. Yes.
You're not using cyclic splines, are you?
Sorry?
You're not using cyclic splines. You're using just cubic splines, but you're not looping around 0 and 24 so that they match, do you?
That's right. Yes. Yeah. We don't do that. Yes.
Seem the coefficients match.
Yes. Yeah. We don't consider that. Yes. Yeah. Because we are using the temperature on each day, right? So basically, it's like the temperature at hour 0 will not necessarily equal to the temperature at day 24. Yeah, hour 24. Yes. Yeah. So we don't have that theoretical constraints. Okay. So we also tried other applications. So this is the second applications. So basically, this application to try to predict the fat contents of the meat samples using functional covariates. So the functional covariates basically is the spectrums of the meat. Okay. So in industry they have special tools called absorption spectroscopy. They can measure the spectrum of the meats. Okay. And so we have this. This is the spectrum of the meats. Okay, looks like. Okay, they have the in different wavelengths. I want to using these spectrums to predict the fat contents of the meat. So this is the results. And again, like you know, the reviewer always want us to try to compare with all the methods available. So we are forced to try different convolutional neural networks and also conventional neural networks and also LSTM. So you can see here, I turn out like again, our neural networks will have the smallest prediction accuracy with I think the standard error are pretty similar across the methods. Okay. So this is the third example. So we want to predict the total amount of precipitations based on the daily temperatures for 35 Canadian cities. And so our input will be this daily mean temperature for the 35 cities. And this is the prediction results. And so again, like, you know, we have a pretty good prediction accuracy for our functional neural networks. Okay. So we do a simulation study. So basically here, we have two purposes for these simulation studies. So firstly, we want to see how well we are able to recover these functional weights, okay, because this is our main parameter to estimate, right? The second thing we want to do how our prediction looks like, okay? So, so we generated some functional observations, and we generated the response based on this model. And so this is how we generate the functional inputs. And so for the relationship between y and the functional varies, we tried like, you know, this is the simulation one will be the linear relationship between X and Y. And the simulation 2 to simulation 4 will be like try some nonlinear functions and to see, whether this functional neural network really wins for this nonlinear relationship scenario. Okay, so then we look at the how well we can recover the functional weights, and also we also want to look at how our prediction looks like. Okay, and so there's one tuning parameter lambda. We have to doing some tuning to be using cross validation to do the tuning. Okay, so this is like how this estimates for the functional weights. And also we look at the prediction. So we tried some bunch of methods to do the comparison, including lasso, random forest, etc. And we look at how the relative mean square prediction errors compare to other methods. So basically, we will look at all these models and we look at finding the minimum of the mean prediction errors, and we look at the mean prediction errors over this minimum prediction error. So suppose the model has the smallest mean prediction error, this will be equal to 1, right? So if the model has a larger prediction errors, this ratio will be larger than 1. Okay, so this is the results. So we tried a bunch of predict models, and so you can see that for functional neural networks, most time it will wins around 1, right? Yes. So this is the comparison. Okay. Yes. So yeah. So for scenario simulation 1s, this is there's a linear relationship between predictor and the response. So therefore, this method is a functional linear regression models kind of also wins in this scenario. But for nonlinear scenarios, our method is always wins. Same with other scenarios. Okay. So this is conclusions of my talk. So basically, we develop a functional neural networks specifically for this functional input, and we find that these neural networks perform better than the conventional neural networks. And we find one advantage for these neural networks is that our functional weights is easier to interpret. So if you want to know the details, you can look at our paper or you can ask any questions. Thank you for attention.
Thank you, Professor. Si vous avez des questions.
I was wondering, how small can the data set? So one thing with deep learning models is that you have to have gigantic data sets.
Yes.
Now we're turning to functions. So in one of your example, you had 102 curves.
Yes.
How large does the data set need to be for the method to give you something, quote, useful? And second related question, how long does it take to train?
Yes, this is a very good point. So like, before I work on these neural networks, I also heard the people talk about, neural network have to require large number of data points. Yes. And so actually I find it surprising for me that this neural network actually working pretty well for small data set as well. So for my temperature Canadian weather data, I only have 35 data points. Yeah, so it's able to do the prediction pretty well and beat like conventional statistical models. Yes.
Is it because of the integrated penalty? So you have this L2 penalty on the
yeah. I'm not sure. Like yeah, I haven't think about like why this working so well with small sample size. I think we still need to give more thoughts what's happening. Yes. So yeah, in terms of the computing time, actually it's very quick. It's comparable to linear regression models. Yeah, it's 1 second, you'll get it. Yes. Yes. Yeah.
Yeah, but maybe a very naive question, but why do you need this smoothness property on the weight? Because I can think of many examples why I don't want actually this content.
Yes, yeah, this is a good point. So the reason we want to put this roughing penalty term there is that you know, as I just during the talk I mentioned that so one problem when we estimate these functional parameters is that how to choose the number-based functions, right? So if you don't put the roughing penalty term there, you need to choose the number-based functions more careful. So this is kind of, you know, we kind of doing it from the other angles. So we, you know, just throw in a bunch of basic functions, and then we doing these roughly these controls to control the prevent any overfitting problems. Yeah. So yeah, I'm not sure like what will looks like. You know, if there's no penalty term, maybe there will be overfitting problems. I'm not sure. Like we didn't. That's kind of our, you know, habits. We want to put the rough penalty term there. But I mean, it's interesting to see what happened without a rough penalty term. Yes. Yeah. Mm.
Any theoretical results on the subject?
No theoretical results. Yes. Yeah. Mm. Okay. Yes.
So a quick one, like I have two questions. The first is quick, like have you heard of neural operators? Because it seems like the idea is similar to have inputs, such that it's neural networks made to approximate operators. So functionals that take functions as input and as output.
Mm.
I think this connection would be interesting to see. I don't know if you're familiar with that. It's like people use more of that in computational mathematics.
Okay.
Like approximate say parametric PDEs. So the application is different, but the machinery seems to be connections. So
yes,
I was wondering if you're aware of that area.
No. So you're talking about like you know, in the math research, they try to approximate any multidimensional functions. Is that?
Yeah, even just operators. So like really networks where exactly you replace sums with integrals, and then you have like layers now become infinite dimensional operators.
Okay.
And there's also a bit of theory for that. So it could be interesting connection to study in relation to your architecture.
Okay. Is this a functional operator related to the neural network as well?
Yeah. These are essentially generalization of neural nets.
Okay.
From the discrete to the continuous.
Okay. That's cool. Okay.
Yeah.
Having a I didn't know that before. It's good to
I think
the connections. Yes.
To check out.
Yes.
The second question I had is like more technical, like you have these weights that now are functions, and now you express them as linear combinations of splines, then you learn the coefficients of the splines, right?
Mm.
So you have the integral of a sum against your function xi, right?
Yes.
So you could pull the sum out of the integral. And so can we think about this as kind of a way to project the initial input functions into a discrete space, and then it's like having a discrete neural net? Is that
Yes. Yeah, exactly. Yes. Yeah, exactly. Yeah. So we add one extra layers to handle these functional inputs.
Right.
Yes. Yeah. Sorry. Do you have any questions?
Yes. Is it easy to generalize it to 2 dimensions in space instead of just time?
Yes. I think it should be able to. We haven't tried that, but I think theoretically should be fine. Yes. Yeah. Yes. Yeah. That's a very good point. Yes.
I was trying to get intuition. So you mentioned that there were fewer parameters in this model than there is in just vanilla deep learning one. But when you parameterize it with spline, somehow if you have capital T time points, then you get something like 3T plus, you know, additional parameters for the boundaries. Is it because, again, of the smoothness penalty that you get fewer parameters than just saying this is a T vector and that there's a parameter for each? Or is it because there's fewer layers that are needed to represent the function?
Yeah, so I guess like really depends on how many basic functions you use. Yeah, so if you using the less number basic function, that if you're using less basic functions, then the number of time points, you will have less number of parameters. Yeah. But if you choose to using the number of basic functions equal to the number of time points will be the, if your number of basic functions equal to the number of time points, it will be the same number of parameters.
Yeah, but the effective number of parameters.
It will be smaller because of the roughing penalty. Yes.
But relative to the deep neural network itself, which is, you know, we treat time as a t vector.
Yes. Yeah. Yes. Yeah, this is a very good point. Yes. Yeah. Yeah. So because we have roughing the penalty controls, so actually the effective number of parameters definitely will be much smaller than the t. Yes. Yeah. Thanks. Yes. Yes.
So I was wondering, how do you think the FNN would perform for cross-sectional data?
For what kind of data?
Cross-sectional data. You have a cross-sectional data, like you're having, you're taking all different observations at the same time.
Okay, like to kind of repeat the measurement. Okay. Yeah. So I guess really is this so when you see cross-sectional data, I guess it depends on whether this cross-sectional or repeated measurement is for the same subject over time. You know, is this a repeated measurements of the curves or is separate? Yeah, in separates, I think that'd be a little bit hard because you know, for the nature of these things, you have to have the curve and the inputs. So basically, you have to measure the same subject over multiple time points. Yes, yeah, that's kind of how this neural network design. Yes, yeah.
On remercie encore une fois.